Welcome to Decoding the Data Ecosystem, a podcast with valuable insights, inspiring stories, and practical advice to guide you on your journey through the world of omics research and how the NIH Common Fund data ecosystem can support that journey. I'm your host, Dr. Allissa Dillman, and I'm the Training and Engagement Director of the CFDE Training Center. My background's in bioinformatics, and I've been working in bioinformatics and data science training and engagement space for almost the past 15 years. I'm really passionate about lowering the barriers of entry for these fields through creative engagement activities such as these podcasts. Now let's get to the show. Today I'm chatting with Dr. Deslattes Mays. She's a mathematician and software engineer by training with a PhD in tumor biology and has more than 30 years of experience in large-scale computing for biomedical research. Hello, Anne, and welcome to our second podcast episode.
Hi,
Tell us a little bit more about yourself. I think it's really cool that you went from software engineering to tumor biology. So I'd love to hear a little bit more about that really interesting journey.
Sure. And thank you so much for inviting me. It's an honor and a privilege to be here talking with you today. So that journey, I actually began life as an abstract mathematician, which really allows you to postpone differentiation for as long as possible. So the tumor biology is the final differentiation stage. My first job actually was as an engineer at a satellite communications company, where I first started writing software for instruments, satellite modems, and I wrote a space segment allocation algorithm that allowed you to share space segment on the satellite amongst multiple customers. And after getting my master's in computer science from Hopkins, I then moved to MITRE. I was recruited there for their large-scale integration of the air traffic control system. In that case, we had built the largest simulation model with a flight simulator of the entire process of flying an aircraft from one airport to another. So it included 24 centers. It included the software for ground control, tower control. And in those days, that was all in large frame computer systems, and in fact, multiple different kinds. So we focused on the interfaces. And the importance of that is that when I started at Tiger, the Institute for Genomic Research, I was recruited because they were looking for a software engineer, and they had no idea what one looked like. And I was Craig Venter's first software engineer. And I did that because actually just life. I was expecting my daughter. I wanted to be closer to home, and they were within 3 miles of my house. So that's how I met Craig Venter and Claire Fraser. And after being there for 1 year and rearranging how they did software and teaching them how to do version control, including Steven Salzberg, Craig thought that I could start his software group at Celera. And so we did that. And I actually recruited a lot of the first engineers from MITRE, where we had done the air traffic control modeling and simulation, because we only had 6 months to build what we had to build. And I had to recruit people that I knew would deliver. And those people, Tim Stockwell, David Smith, Carl Dahlke. David Smith was part of the import database, if you know about import. So, and actually many people who are at NIH today were in my engineering team. So what do you do after you sequence the human genome and you have sequencers up 24/7? What are you going to do? So I decided to get my PhD. And I wanted to work in a particular area. I wanted to work in pediatric cancer because of personal losses that I had experienced. And that's what I decided to point my head to. And that's how I got to where I am now.
That is a really cool story. Thank you for sharing. Is there something in particular about biology that really sparked your interest? Was there anything about it that was very unique compared to more of the computer science side of things?
So everything I had done beforehand was man-made. And biology is more complex. The first rule of software engineering is you have to understand the domain. And the domain of biology is so complex, I ended up getting my PhD in it. And actually, as part of that, I got exposed to new measurement technologies. And that was very satisfying because my father was a subatomic quantum metrologist. He invented new measurement technologies. He was both a theoretical and an experimental physicist, and was the first one to put together laser light measurement with X-ray interferometry to improve precision. For my PhD, I used long read, unfragmented mRNA sequencing technology on PacBio to using this new measurement technology to discover new transcript isoforms. So it was very gratifying.
It's funny how we end up following in our parents' footsteps in really interesting ways. My background started in biology and ended up more in technology, but my dad was an electronic technician by training and was constantly pulling things apart. And my first running of the Illumina sequencer, I became really fascinated with technology as well and ended up doing way more of that. So that's really cool. So I actually originally met you at BioIT many years ago, but then our paths crossed again when you were part of the Data Scholars program that I was helping to run. So I'd love to talk a little bit more about your experience with the Data Scholars program, because this is where you really started to interact a lot with some of the CFDE data sets while you were at NIH.
Yeah, it was really, again, an honor and a privilege to serve as the Data and Technology Advisor Scholar for NICHD, given my PhD focus. And I was able to, my mission was to bring researchers to the data. And we were able to do that because of the platform as a service that they used, Cavatica, that is the front end for both Kids First and Include. And that's when I started. Actually, it was probably the third time I taught my Elements of Style course. And the feedback that I got on that course, it allowed me to onboard researchers with no prior command line experience to do computational analysis at scale in the cloud. And my favorite researchers to onboard were those enthusiastic researchers who felt the barrier to entry was too high. And by doing this Elements of Style, I gradually demystified from command line to Docker creation to creating containers for processes, teaching them how to stitch together workflows, and then running and executing them so they can do new discoveries on Kids First data as well as Include data. But that platform as a service really revolutionized things. But at the end of the day, the same principles of software engineering are required, which is you should make processes small and containerized and stitch them together with reinforceable methods that the workflow languages empower us to.
So you mentioned the elements of style, and I think this is something that's not necessarily something we come across in bioinformatics even at times. So I'd really love to kind of hear how you define elements of style sort of in the context of biomedical research.
So the first time the Elements of Style shows up is in an English grammar book by Strunk and White. It was written in 1919. At the end of First World War was done, and a student, E.B. White, took a course called English 8 taught by William Strunk. And this little book, it's very small, is full of pithy phrases. And these pithy phrases are small little clues to demystify the work of making. So a pithy phrase is a statement that is brief but full of substance and meaning. So fast forward, what does that have to do with software engineering? So this small little grammar book, a few rules, contains all you need to know to write proper English grammar. Now, Brian Kernighan, when I first started doing programming in C, Brian Kernighan, who is the author of the B language, the C language, together with Dennis Ritchie, wrote the C programming language, but he also wrote the Elements of Programming Style. And that is built on, the philosophy, what can be taught with a few simple rules. And that's what I turned into my course as well. And I actually contacted Brian Kernighan to tell him that I was doing this in biomedical research. He's about 83 right now. He returned my calls and was so happy to support me, and is actually going to review the book that will come out on the Elements of Programming Style for Biomedical Research, workflow creation. He will be an editor for that. And so I'm excited about that. But I asked his permission to use the phrase because I thought he should grant it. He goes, he gave me all the permission to do. So I have 10 rules. If,
Oh, um, are there two or three in particular that you'd like to highlight? And we'll definitely link the rest in our podcast.
um, okay, I'll use two or three. Write clearly. Don't be too clever. What does that apply to? It applies to everything. When you do software engineering, oftentimes you've got people writing these small little quick things, but they were illegible and impossible to parse out. So it should be simple and straightforward and easy to understand. Modularize. In C, you would use procedures and functions. In our world, where we have workflow languages that stitch together containerized algorithms, containerize. Take the small algorithm that is doing a single function, containerize it, identify and write down your inputs. What is that process doing to transform your input to an output? And then use workflow languages. Don't write your workflow in another language. Use a tool, use a workflow language that is made to do that. And why do we want to do that? Is because then the workflow language takes advantage of the underlying machinery. So we layer our concerns in the appropriate way.
So you've talked a little bit about containerization a couple of times now, and I'd like to hear a little bit more specifically about containerization. So that might still be a new concept for some of our listeners. So just like a brief chat about containerization in particular, I think would be really cool.
So today, so back in the day when we had functions and modules in a monolithic system, we would containerize by making a library function. You know, the software engineering principle is a fan in and a fan out structure. You should use libraries, you should reuse tools because that is testable and efficient. These days, we achieve that through something by using something like a Docker container or Singularity. And the Docker, but you can always turn a Docker container into a Singularity. That's a technical detail for another course, but what you do, a Docker is like a little mini operating system with all the tools, the minimum set of tools you need to execute a process. So if you have a bare bones virtual machine, let's say I want to call up a virtual 8 CPU, 8 GB machine, that's a very small one, but I have to put the operating system, so Linux, and usually I use Miniconda, set up the environment, get the environment right, then import my tool. If it's available on Anaconda, I set it up that you read in your requirements.txt right into the Docker instructions, and then you build it. And with GitHub Actions, you can actually automatically build it, and you actually can deploy the image onto GitHub so that you can pull it into your workflow. So containerization is creating the environment, creating the Docker container, which then creates the image that then can be used in a process. That's what we do today, where we used to use libraries.
So that kind of brings me to this idea in general about, bioinformatics and documentation and the role of documentation in making bioinformatics project more reproducible and accessible. So I'd love to kind of hear a little bit more about your thoughts on how documentation, containerization, and other tools can help us with this reproducibility and accessibility.
So Brian Kernighan taught me well, and nothing is done until you've documented it. And for every line of code, there should be an instruction. It shouldn't, so literate programming is exactly that. And that predates Kernighan and Ritchie. And I'm blanking, but I'll come to it later. The man who really set this up. But literate programming, I break our world up into two parts. One is the batch processing, where containers play a huge role, and the other is interactive. So after you've transformed your vast amounts of data, that's why we have to do batch processing. Genomic information is large, usually has to be transformed down to the nuggets necessary to do analysis. JupyterLab notebooks are a fine way to do literate programming, where you can write markdown language that explains what you're about to do, explains what you're going to do, and then the code, whether it's Python or R or Go. you can actually write in any language that has a kernel in a JupyterLab notebook. So literate programming, you're actually writing for your future self. If you don't want to write for others, protect your future self. You may be very clever and get your work done in, in a day and you have it all done, but a year from now, will you know what you did? And that's why you and I know we want it to be reproducible and findable. That's not just for your friends and neighbors, that's for yourself.
I think to your point, Anne, it's also very common, especially in the bioinformatics world, to do something once and then do a whole bunch of other things for that story and not do that thing specifically for like a whole year. And then you move on to your next project and now you have to do that thing again. And more often than not, it's been a year since you've done that very specific bioinformatic process. And then you're like, oh no, I now have to re-remember, relearn, reteach myself. So you're exactly right. Um, if you make good documentation, it's helpful for future you too, because at some point you are going to do it again, but it's going to be a ways away and you're going to forget how you did it.
And I think what's really fun these days are the means by which we can get it done. So the NICHD Elements of Style course I taught for Kids First and for Include is still on the NIH website. And that is, I go back to it often because I forget myself. Okay, so I'm at scratch from on my terminal window, about to kick off a GitHub. I want to put my software up on GitHub. How do I do that again? What are the three things I need to do? I go to that site, I find it, I go, okay, cool, 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 cool. And it be, like if you're not doing it every day, your brain doesn't remember and you need these things. So the other thing that's really helpful is the ability to make documentation. So that GitHub site I made with MK Docs. A lot of people use Sphinx, and you can have then well-documented code in the, if for those who aren't familiar, just look up any read the docs. And what you have right away is not only well-documented code, but a user guide and almost a basis for tutorials. And so I try to execute that discipline. And this is what Kernighan taught. It isn't done until you've written it down. What did you do? And otherwise, it's actually not taking yourself seriously. So what if you got it done once? If you get it done twice, that shows you really know what you're doing. And if you get it twice, then you've written it down and you're able to explain it to somebody else, you're golden.
So, what do you think are the most common barriers to reproducibility that researchers encounter, and how do you think that we, as people in the field that are help supporting research and training and things of that nature, can use to help address this?
I think it really does come down to some basic things. Use a repository, use markdown languages to document what you do, and and think of your future self. So the barriers to entry, actually, there are so many. Sometimes it's just like I said, researchers who have a biomedical question to be answered, and these days it is difficult to do without knowing how to do computational analysis. So lowering that barrier to entry means don't be afraid to teach that researcher command lines or Jupyter. And I think the Jupyter Lab Notebook is fantastic. Demystify the content. You don't have to know everything. What is your question? Start there. And then how are you going to answer it? And as you help a researcher on board, lower the barrier of entry of technology, lower the barrier of entry of computational analysis in the cloud. Let's talk about the Kids First and the Common Fund data ecosystem. All that data is up on Amazon and Google buckets for the most part, right? So the Kids First data managed, funded by NIH, but is actually managed by CHOP, the repositories. Access is handled through dbGaP for GTEx, for Kids First. You have to apply with your research question. All of those steps are overwhelming. So we have to, teach kids, teach researchers and clinicians alike. It isn't so complicated. Common sense steps. It's just a lot. Using platforms as a service also help remove that barrier of entry. I've been doing cloud computing since it was available, and the platform is very high. You had to be engineering capable. Now it's lower, 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 lower. You do need to know a few things, but you don't know with a platform as a service, you don't need to know how to spin up a machine, what to do when it's up, how to kill it, which is important so that you don't run out of money. The platforms have automatic shutoffs or can manage the costs, and some do it better than others. And they also reinforce reproducibility, pulling it from a GitHub repository. A lot of the workflows that are on the Kavatica platform, which is the front end to Kids First, are on GitHub. And so you're pulling in a known version, and each of those are using containers that are Docker images that are at the basis. So you are achieving a beautiful success. So there's a lot of barriers, but through education that is focused on a research question, I have had great success in lowering those barriers of entry.
So let's talk a little bit more about the Kids First data set. What do you think makes it unique compared to other data sets in sort of the omics field that we work in?
The focus on pediatrics. So fundamentally, pediatric illnesses are rare. So these are rare conditions, from congenital heart disease to um, a lot of brain tumors. So they just released a large data set of kids' brain tumors. It makes it a unique location of harmonized data that you can build cohorts large enough to discover new things. And once you're at that point, one of the things I was trying to persuade NIH to do is act as our provost, so to speak, internationally, so we can grow those data sets, link them with Genomics England or with other data sets that are available worldwide, because we know the biggest challenge with finding solutions, whether they're genetic or other omic discoverable, is getting a cohort large enough with the condition. So the Kids First unique aspect is this access to rare and pediatric data sets.
And how do you think that the resources kind of around Kids First, not just the data, but sort of the resources as well, help support reproducible research? Like, which kind of tools and features do you think kind of enhance this specifically?
The ability to access a platform as a service out of the box, and that allows you to do more in a collaborative workspace, use Jupyter Lab notebooks, put them into GitHub. It requires a little bit of discipline to do that. Other platforms do support direct pull from GitHub, but Kids First, the cohort browsing, the direct push the data to a platform allows you then to quickly run analyses. I use Kids First and include data sets to do a alternative splicing analysis with RMATs, and that has become a basis of 2 years of analyses. So analysis takes a long time, and getting that data processed and supported by a platform, it's really it's necessary for us to really take full advantage. And I'm so glad, because it is right to store the raw data so that you can actually reprocess, because we reprocess the data, even though it's already processed in some respects for you, but the ability to access that raw data through the platform allows you to do things in new ways that maybe haven't been done before.
That kind of brings me to my next question, which is what role do you think community collaboration plays in driving reproducible research, especially in large scale data sets like Kids First?
Being able to collaborate in a workspace. And actually, we didn't talk about something that I'm going to mention that we should talk about, which is diversity and inclusion. And I want us to talk about that because one of the things I learned in teaching this class is that, you know, not every university and college in the US is a Harvard or an MIT or a large, well-funded site. So they don't have a high performance computing infrastructure, and having access to these cloud resources with credits and the ability to access to get more credits makes the ability to do analysis available to the less fortunate colleges and universities in our country and worldwide. So just a sidebar, we shouldn't forget about that. But now I forgot your question.
No, that's okay. Well, it's partially about that, right? So I was asking about community collaboration and what role it plays in driving reproducible research.
And I think there are two parts. So not only reproducible research, but ideas. I actually think creativity happens when two or more of us are gathered. Like I believe consensus building, multiple people having a think about things allows you to do more clever work than you would do if you were in isolation. So this ability to share a workspace, to collaborate, and to actually brainstorm and come up with new ideas, new ways of looking at the data is a fantastic way to improve the health of children. And why pediatric cancer? I have to tell you, I was motivated by Dr. Ching Lau. So Ching Lau gave a talk at Jackson Labs and said, we are 100% failing our children. 100%. Why is that? Because the current methods and treatments have long-term lifetime effects that we are not fully accounting for. One of the things I really enjoyed about the Include project is that phraseology. It's the study of individuals with the condition of Down syndrome across their lifespan. We should do the same with pediatric cancers. We should study the condition of a pediatric patient who has a cancer across their lifespan because it would change our perspective. What motivated me to get my PhD in tumor biology was the loss of a young boy who was born with a glioma. And he passed away at 18 of a tertiary cancer. And that happened because of the treatments and the lifetime effects. It's a combination of things. He was born with a genetic defect in his DNA repair genome. So, but that notwithstanding, it was contributory because of the non-specific aspects of most treatments today. It causes universal damage. So reproducibility, we do not want to redo already done analyses. We must be certain about our results. Therefore, it should be reproducible. If you do it once and you can't do it twice, it's not done right. And so it's actually for the integrity of the research that we do this. And at the end of the day, don't forget it's a patient at the end of the day. These are people, and we're trying to improve their lives. So let's take that seriously.
So you said you wanted to circle back around to a little bit more on the diversity and inclusion topic, and I do actually really like that idea because I too think that some of these tools and platforms and technologies, when set up correctly, can actually really improve access and ability to do really complex computational work, even if your school institute doesn't have the support for you to do that sort of locally. So I'd love to hear a little bit more about that too, because that's something I'm really passionate about.
When I first started giving these classes of elements of style, there was a state college in Florida, a participant from that college, and this class, we were able to, because I had enough support on this, to give a lot of one-on-one attention so that they could keep up. Because the previous experience, they no command line experience, no experience of using tools that are web-based that give access to computational tools, but it changed their minds and made them think bigger. That this allowed them the access to the data, the access to the compute, the access to the ability to do the analyses, made them imagine a new program at their university. And that, because they said, well, we could then apply for these grants that they thought they couldn't apply for because they didn't have the tools or the infrastructure to support them in their work. So that's what I like to see is because, discovery is going to come from diverse corners. It's not always going to come from the person that was lucky enough to be able to be in the best university that's the most well-funded. I think anybody could find a new cure for anything if they've got the right tools and imagination and support.
That's really awesome. So I just want to sort of close with two last questions for you. The first being, What advice would you give to early career researchers or students entering this field about building good habits for reproducibility and handling large data sets like kids first?
I would say take yourself seriously and make sure you're adhering to best practices, which is learn early and often to use GitHub. One best practice is you should check in your work daily. Do your work, put it into a repository, even if it's not perfect. Don't worry about it. It will evolve. Pseudocode can be a text file which says, okay, I imagine I want to do X, Y, and Z. Write it down, put it into GitHub, and then build from there. The second is look at you and I. You started in the more on the bio side and moved to technology. I started on the technology side and moved to bio. I think that that's critical to do it. You shouldn't be one, you should not neglect one for the other. Understand the biology, understand the context of the biology. If you don't know, look it up. It's all available and can be demystified. On the technical front, has it been done before? Don't reinvent the wheel. Check and see what has already been written. Don't write a new software program if you don't need to. So build on the shoulders of giants, use testing, use continuous integration. Testing, GitHub Actions can help you. What is testing? You write a line of code, you should test that line of code. Does that code do what you think it does? So, yeah, those are my thoughts.
You've had so much good insight and really useful information, and your passion for reproducibility is very clear. But I love to end with sort of a fun question. And since you and I are both RNA people, I like to ask, do you have a favorite gene and why?
Oh, very interesting. EEFA1A1. This is an elongation factor. Why I like it is one of the ones that I just in my PhD work through the long read on fragmented RNA sequencing with mass spec, I was able to find a novel isoform. So this elongation factor, it plays a central role in healthy human bone marrow. So my work worked on healthy human bone marrow. And one of the actual, that's like the tip of the iceberg, but one of the things we discovered, and it seems obvious today, but in the stem cell population of healthy human bone marrow, it is more diverse than the differentiated bone marrow population. Why is that important? And what's up with this elongation factor? What we discovered is almost the postal codes for the RNA in your stem cell population lie within there so that those cells go to a specific destination. Um, I don't know if this elongation factor is one of the ones that goes to that specific destination, but it definitely has a place in my heart. Terminal differentiation means that you can't de-differentiate and become something else. So my PhD is in tumor biology. I did say that I started in abstract mathematics and I postponed differentiation. Terminal differentiation, I'm not sure, but
I think that is a great way to end our podcast today. Thank you so much, Anne, for talking with us. We really appreciated all the wonderful stories that you shared with us today, and we appreciate your time. Thank you so much for being with us today.
thank you so much, Allissa. Always a pleasure. Look forward to our next hackathon.
You have been listening to Decoding the Data Ecosystem, a CFDE Training Center podcast. Be sure to check out our other episodes in this series. Find out more information about CFDE data and tools that may be valuable to your research by visiting our website.